Hello and welcome to the first Galvanizing webinar. I am Ken Landau. I'm a staff engineer with AIST. This webinar will feature an overview of first the resistance welding process and equipment utilized in coil joining, including basic resistance welding principles and seam and spot welding techniques and equipment. Second will be the laser welding for coil joining. Excuse me a second. For coil joint, alternative configurations of laser welders and key control elements in the weld program. And the third will be a summary of current technologies that can be used to assess the quality of the welds and introduce a new technology under development that has the potential to provide an alternative for inline inspection. As with all AIST functions, we must first go through the antitrust guidelines. So please do not discuss with others yours or your competitors' pricing procedures, or anything that might affect pricing, such as costs, discounts, terms of sale, or profit margins, and anticipated wage rates. Do not make statements about your own pricing or those of your competitors, and do not talk about what individual companies plan to do in particular markets or with particular customers. Also, with the webinar going on, all of the attendee audios are disabled. We are looking for questions and answers during this, but we will try to wait till the end to answer those. But if you do have a question, please use the Q&A function that's in Zoom. It's at the bottom of your screen. The host or myself and the moderator, which I'll introduce in a second, will be screening the questions and being able to then present them to the presenter. This session will be recorded and it will be available on demand replay on AIST's website. If you're having any technical difficulties, please contact training@aist.org. And an important reminder, photos or recordings of this presentation are strictly prohibited. You'll be given a link to access the presenter contact information and recordings following the end of the webinar. With that, I'd like to introduce our moderator, Nikhil Kulkarni. Nikhil is the product metallurgist at SDI in their Jeffersonville facility. And with that, I'll pass it off to Nikhil.
Good morning, everyone. Thanks for attending. And this is a new way of our meetings, I guess, for hopefully a very short period of time. I recently became the chair of the Galvanizing Technological Committee, and I'm proud to be chair and also the vice chair before, and keep the baton going. And we want to keep the technological conferences every time, and want to gather more knowledge of the latest developments. And today, strip welding is one of our topics we would like to start with. And we have 3 good presenters with us waiting here. And like Ken said, if you guys have any questions and answers, I'd like to moderate that. And we can decide when we can, I can ask the questions for you once you have put it in the Q&A session, Q&A box, and we'll take it from there. All right, thank you. So I'll start with introducing our first presenter over here, Mr. Blake Ryan. He's the Vice President of Sales and Marketing at Taylor Winfield Technologies. Blake holds a BA degree from the College of Worcester, as well as various business and technical certifications earned throughout his career. He has been with Taylor Winfield for 25 years, holding various sales, marketing, management, and senior management positions. He is currently Vice President of the Coil Joining Product Group. He's going to present on resistance welding utilized in the coil joining process. Are we going? Okay. Our next topic would be on laser welding for coil joining by Mr. Denny Belay, sales agent of Hugo Maybach. Denny Belay holds a diploma in mechanical engineering, design from Mohawk College, as well as certificates in business and metallurgy from McMaster University in Hamilton, Ontario. He worked at ArcelorMittal Dofasco for 33 years as a reliability engineer, where he developed his knowledge in various coil joining technologies. He became an internal corporate consultant with ArcelorMittal for laser welding. He's president of Belay Consulting and is currently the Hugo Maybach sales agent for Canadian and US markets. Next. Mr. Alex Nadeau, Chief Executive Officer of Technar. Alexander Nadeau has an engineering degree in physics engineering, a master's degree in applied physics with a specialty in laser ultrasonics, and an executive master's in business administration. He worked as a photonic engineer on laser ultrasonic applications at Technar from 2004 to 2008. In 2009, he became responsible for a new product line based on laser-induced breakdown spectroscopy applied to real-time molten metal composition analysis. In 2015, Nadeau replaced his father as Chief Executive Officer of the company. Alex is going to present on current and upcoming technologies for weld quality verification. I welcome all you presenters. Really happy for you joining us for our first webinar conference for the Galvanizing Technical Committee. And we look forward for more such committee meetings like that until we're allowed to have meetings in open. But I think we should go ahead, Ken, now.
Okay, you want me to go ahead, Nikhil?
It was a little weird talking like this. I'll give it to you, Blake.
Okay. Just share my screen. Okay, good morning, everyone. It's our pleasure to be here at the first webinar, AIST webinar meeting. A very historic meeting for a first. So thank you for that kind introduction, Nikhil. And for my part of the presentation, where I'm going to talk about coil joining and strip processing lines using resistance welding. My presentation subject will include the basic principles of resistance welding, two common types of resistance welds, spot and seam welding, types of strip processing lines that use resistance coil joining welders, and common types of resistance welders used in strip processing lines. So we're going to start with the basic fundamentals of resistance welding and then tie it into the steel processing industry. So the first question is, what is a resistance welding? Resistance welding is the fusion of metal created as a result of pressure, heat, and time. Pressure is applied by electrodes to two overlapped pieces of metal. Current is passed through electrodes into the overlapped metal, which causes localized fusion called a weld nugget between the two pieces. You can see on the image to the right, the two copper-looking pieces are the electrode, and that bright, shiny part in the middle is the weld nugget that's being formed between the electrodes. So the next question is, how is a resistance weld made? The weld is made by passing current through two pieces of metal held in contact using weld force applied by welding electrodes. The electrodes serve three functions. They hold the part together under pressure. They provide a path for the welding current to pass into and out of the workpiece. And they are cooled to prevent material from sticking to the electrode and minimizing distortion at the weld interface. This is a video of a weld being made. It's in 2 times slow. So the yellow parts that you see above are the electrodes, and the weld nugget is being formed in the metal between the 2 electrodes. You can see the heat being generated between the 2 electrodes and the beginning of the weld nugget being formed. That beautiful looking weld nugget that's spinning and being formed is actually molten material that's being created between the 2 electrodes. So the electrodes will stay in place with force, and you can see the heat that's being dissipated into the electrodes. And then after the nugget is formed, the electrodes will release and the material is joined. So that is a spot weld. The second type of resistance weld we're going to talk about is a seam weld. Seam welding is very similar to a spot weld, but it's used, there are 2 round electrodes that deliver the current to the workpiece. So seam welding is the process of making a series of spot welds with a pair of rolling round electrodes called welding wheels. In resistance seam welding, a silicon-controlled rectifier, or SCR, is mounted in a weld control that turns the welding current on and off at predetermined periods of time, of heat time, as the weld wheels move across the workpiece. Each heat time produces a weld nugget that you saw before in the video. Cool times separate the nuggets into what is called an interrupted seam weld. The cool times cause the nuggets to overlap each other, which produces a continuous airtight seam between the workpieces. And whether or not the electrode, whether or not the nugget is spaced far apart or overlapping depends on the application. In most airtight or watertight containers that are sealed using resistance welding, seam welding, the nuggets are overlapped so that the container or the vessel is airtight or watertight. Whereas maybe some piece of structural steel used in construction doesn't need the weld nuggets to be overlapped. It just needs the weld strength. So the nuggets would be spaced further apart. So the types of steel process lines that use coil joining resistance welders include coating, galvanizing, coil buildup, pickling, cold rolling mills, coil plating. The coil joining welders are used in virtually any continuous process line to enable that line to run 24/7, 7 days a week, and 365 days a year, except for maybe a couple of weeks of maintenance downturn. The common types of resistance welders used in strip processing lines include a resistance spot welder, such as the one shown on the left, or a resistance narrow lap seam welder, which in the industry is sometimes called a mash seam welder. The coil joining spot welders, with coil joining spot welders, the resistance spot welders for coil joining are designed to create a weld between 2 overlapping coil ends. The weld is considered a transport weld, since the resultant weld joint is equal to the 2 strip thicknesses being joined, with no reduction at the weld interface. In this case, the weld is normally removed at the exit end of the process line. As previously described, the electrodes travel across the strip ends, pausing periodically to create a predetermined number of weld nuggets with sufficient joint strength to transport the weld through subsequent line processes. This is a video of a roll spot seam welder. The electrode heads are lowering. They travel across the overlap between the two steel sheets. And whenever you see the weld head stopped, a weld is being made. So when it's moving, that's called the cool time. And so in this case, we're making a series of spot welds across the strip overlap. So the overlapped roll spot weld looks something graphically like this. There's a series of welds across the strip. There's a nugget that's formed during every heat cycle, and the material is 2 times material thickness. This is an image showing an actual weld that has been created with the roll spot coil end joiner. In this case, the customer needed 2 rows of spot welds to ensure that they had sufficient strength for the weld to hold through the process line. In the case of resistance narrow lap seam welders, a resistance narrow lap seam welder creates a smooth, thin, and ductile overlap welded joint. The strip ends are narrowly overlapped and electrical current is passed between them using welding wheels to create sufficient heat for fusion. Pressure is applied as the weld wheels travel across the overlapped strip ends, resulting in a welded interface with near 0 weld over thickness across the strip material. The weld seam can pass through the processing line, generally without creating damage or requiring changes to the line operating parameters. And then depending on the type of the process line, the weld may or may not be removed at the exit end of the processing line. A narrow lap seam weld graphically looks something like that. It's near parent metal thickness after the weld is made and is sufficiently strong to hold through the process line. This is a typical narrow lap seam welder. It's what we call a twin lap narrow lap seam welder, which was designed originally for joining advanced high strength strip materials. So let's show you the sequence of how a twin lap narrow lap seam weld is made. In this image, the horizontal blue lines represent the strip material. So the strip ends are stopped in what's called the welding shear gap in between the entry and exit clamps. The clamps are closed. After the clamps are closed, the lower part of the shear carrier moves up to make contact with the underside of the strip material. The upper shear then comes down and cuts the material. Once the strip ends are sheared, they're squared to each other and ready for overlapping. In this case, the exit side, called the exit pivot clamp, moves up, and the entry clamp moves forward, which creates, and then the exit clamp pivots down, which creates the overlap between the 2 strip ends. Once the material is overlapped, the exit clamp pivots down to make the overlap, and the strip end is ready for welding and planishing. Here is a typical machine cycle. So the clamps are closed, the exit shears the material, the entry clamp moves in, exit clamp pivots down, and then the welding carriage drives the welding wheels across the strip material. That happens to be 2 pairs of welding wheels. And the small silver wheel following behind it is called the planish wheel that just simply polishes off the weld and make sure there's little or no weld over thickness. So this is the sequence moving across the strip material, making the weld. In this view, you can see the current being created in the overlapped interface between the head and tail end of the strip material. And then once the sequence is done, the clamps will open and the strip will be released to flow through into the process line. So this is an example of a sample of a narrow lap seam welded joint. It's clean, it's smooth, and there's near zero over thickness. My last couple slides will talk about today's strip material and what's called post-weld heat treatment. With today's advancements in material strengths, steel has higher strengths and carbon equivalent values that can make the weld brittle after joining. Post-weld heat treatment is often added to the welding process to restore ductility to the weld without sacrificing weld strength, and to ensure weld integrity to prevent weld breaks downstream in the process line. An induction heating power supply and coil are added to the coil joining process. And in my last video, you will see the process operating. So the weld wheels are going across the strip material, making the weld. And trailing behind is a very long induction heating coil. The red parts that you see are the induction heating coil. So after the welding sequence, the clamps will reposition the weld to the center line, and the induction heating coil will be lowered to then induction post-weld heat treat the welded interface. After the post-weld heat treat sequence is finished, the clamps open and the weld is released into the process line. So thank you for your time today. I hope I kept it within the time limits required, and appreciate your participation in this webinar, the first webinar for AIST. So if there are any questions, I'd be glad to entertain them.
Thanks a lot, Blake. Everyone, if you have any questions for Blake, you can type it in the Q&A section over at the bottom of your screen, and I can ask that questions for all of us on your behalf.
Oh, there was one.
There's one. Okay. So the first question is, what is a typical post-weld heat treatment time cycle?
Usually the actual sequence itself is, the heating sequence is 15 seconds or much less for thinner material. Overall, the sequence is roughly about, say 20 seconds. What you saw was actually a live video of the sequence itself. So that was in a customer's process line. So you get a sense that it's a very fast process. The big difference between, or what you saw there, is we are post-weld heat treating the full width of the material. So we're actually controlling the heating and cooling of the material based on the material the customer, the strip material, the customer is processing in their line. I hope that answered the question.
Okay. The next question is, what is the thickness? And there is, I think I can combine one more question to it. And someone is asking, they have a pyrometer looking at the exit of the weld wheels. What is a good temperature profile?
The temperature profile is going to depend upon the thickness of the material and the type of the material being processed. So there's no one fits all recipe, and some of those weld temperatures need to be validated when creating the parameters needed to join the material. So there's no canned answer, unfortunately, to that question.
I think I would have time for one more question. Can you elaborate on the importance of planishing?
Certainly. Depending upon the planish wheel sets down the weld and minimizes the weld over thickness. There are many welders out there. The first spot welder that we showed would never have a planish wheel. A planish wheel is typically only used for a narrow lap weld, and my friend Denny is going to talk about it perhaps for laser welding. But the general purpose of the planish wheel is to minimize weld over thickness and to work harden the weld by the planish wheels.
Okay. We'd like to move on to the next presentation. I know there are some questions which have been left unanswered, but we want to keep this whole thing within the time limit. So Blake, we might have to get you back to answer those questions. Until then, I'll note down and try to combine all these questions into more shorter format. But right now, I think we should be moving on. Is that right, Ken?
That's fine, Miguel. I'm going to be here for the duration.
Okay. And you can also look at these questions, Blake, and you can prepare your answers, and then, we can, at the end of the whole session, we can answer them if we have time remaining.
Okay, that's fine.
All right. So our next speaker is Mr. Denny Belai, and he's going to present on laser welding for coil joining.
Well, good day, everyone. I am Denny Belai, and I'll get into my presentation momentarily. Hopefully everybody has it on their screen at this point. So I'm going to go over the subject of laser welding for coil joining. I'll start with a brief introduction of myself and the company I represent. I'll get into a short history lesson, very short. It'll be included where I get into the reason why you would consider a laser welder for your coil joining application. I'll provide a quick overview on the welding process itself, and then look at key factors involved in achieving the best results from the laser welding machine. There's a couple of basic differences in the configurations of the laser welding machines, and these will be touched on. Finally, I'll look at what goes into a weld recipe and the problems that may result if things go wrong. So let's begin. So who am I to be talking to you about laser welding? Besides what you've already been told, I can add this, that I've got about 20 years of working experience with industrial lasers. I've worked on developing laser cutting using solid state lasers, as well as developing the welding process and reliability systems for a CO2 laser welder. Now I'm the sales agent for Hugo Meebach welding machines here in Canada and in the US. Now for the brief history lesson. Laser welding has been in use in the steel industry since 1991, when Hugo Meebach put their first laser welder into production in Rockport, Indiana. Since that time, over 213 laser welding machines have been put into service by Meebach alone, and this does not account for other laser welding machine manufacturers. Now that you've had some background information, you might ask, why would anyone want to consider a laser welder to join their coils together? Mostly that comes down to their capability to weld practically any steel together quickly and reliably. The technology not only has an inherent wide range of weldability, but it's also easily adaptable or flexible enough to work with other welding tools. Let's start with weldability. Laser welding enables the coil joining process to weld the widest variety of steels. It's the most capable process for joining different steel grades and cross sections to one another. It can weld hot band or tin plate and all varieties of finished products in between. The process itself is minimally disruptive due to the very small heat affected zone. It is very conducive for inline heat treatment, so to maintain ductility in the weld with a minimum disruption of the cycle time. Wire feeding is also easily adopted to laser welding process. This allows for the dilution of the hardenable material from the weld, thus maximizing the capability of the welding machine. Now that you've had some background information, you might ask, why would anybody want to use a laser welder for joining coils together? Mostly that comes down to their capability. They can weld practically any steel together quickly and reliably. The technology not only has an inherent wide range of weldability, but it is easily adaptable to, or flexible enough to work with other welding tools. I already said this. I think I went backwards. Here we go. Flexibility. Laser welding can be used for very light gauge or heavy gauge products. The lightest gauge products that Mebach laser welders are capable of welding goes down to about 0.08 millimeters. That's about 3/1000ths of an inch. Other Mebach laser welders, and I can't speak for others, are working with materials up to 10 millimeters. I worked on one Mebach laser welding machine that could weld up to a 3 millimeter gauge differential. So it could weld 2 millimeter steel to a 5 millimeter steel, not something that you would want to do with maybe a resistance welder or other types of coil joining methods. This same machine could handle material down to 1.8 millimeters and up to 7 millimeters, all in one package. It's a heavier machine. Checkerboarding to get the right material combination handcuffs production and how lineups are scheduled. The combination of the weldability of the laser welders and their flexibility opens up possibilities for line scheduling. Fewer scheduling rules enable the process to be more productive. Coil takeoffs or lost coils do not necessarily result in production delays with a laser welder. With the increased availability of the higher laser power and the introduction of faster drive systems, laser welding machines now have surpassed other welding processes in the coil joining field. Cycle times of under a minute are quite common in heavy gauge applications. The reduction in cycle time not only increases the productivity and throughput, but allows line builders to use shorter loopers to reduce capital costs and minimize footprints for their new process lines. Laser welders produce no over thickness. The welds are flush with the surface of the parent material. Welds can be rolled in cold mills or temper mills without opening gaps or producing off gauge. Coating or painting lines do not need to be disrupted as the weld passes through the process to avoid damage to roll coaters or other equipment. Line stops or slowdowns are not required oftentimes when the customer will accept welds in coils when the laser is used. On high-value products like electrical steel, silicon steels, and coating in tin lines, the additional cost of a laser welder often is justified in less than a year if you look at the ROI. And that's just from the increased yields. So laser welding product produces the strongest, most reliable welds in the industry. Weld break rates of less than 1 in 1,000 are reported by Mebach customers on lines that have cold mills attached to them. First-time weld rates of greater than 95% on pickle lines and over 98% on cold rolled products are achievable. Laser welders do not necessarily need constant maintenance or production stops to keep the welder running. There's no welding wheels to be redressed or trimmer bits to be replaced. Typically, a laser welder needs minimum maintenance between schedule outages. The laser welders do have their own unique specialized maintenance requirements, but overall cost for maintaining a laser welder in the current state of development is hardly more than a resistance welder. Laser welding can be the most capable of all coil joining processes. That capability can only be sustained by providing a stable machine, otherwise it will turn into your biggest nightmare. There are a lot of moving pieces in a laser welder with sensitive optics that have a low tolerance for dirt. When these parts wear or the optics degrade, the capability is quickly lost. A good machine design is strong and simple to work on. A machine that minimizes wear points has long-term benefits in sustaining that designed-in performance capability. Reducing sources of contamination while protecting the optical components from weld fume and spatter will extend life. Components will still wear and optics will still get dirty. A well-designed machine that provides easy access for maintenance will help ensure that these tasks are done with a minimum of downtime and produce high reliability. Laser welding is similar to seam welding or resistance welding that Blake was just talking about. The strip still needs to be positioned with a pinch roll and centering guides. So it's very much the same in that way. The ends of the strip still need to be cut and squared off in preparation to be joined. The differences come in the geometry of the cuts and the type of energy used to fuse the material together. In laser welding, the heat source is derived from focused laser light energy. The profile of the cut needs to be extremely square. So the laser welding process begins with preparing the strip by cutting the ends and positioning them under the path of the laser beam. The laser is focused down onto the joint between the two strips. The high power density of the laser light energy vaporizes the metal as its focused beam traverses across the joint. The metal cools and solidifies and forms a seam that joins the two pieces together. The result of a laser weld can be seen in this profile of cross-section. You can see the complete fusion with a small heat-affected zone. Here's a picture of a laser weld as seen from above. So the laser welding process requires very accurate and precise positioning of the strip and the laser beam. Starting with the cut profile, it must be nearly perfectly square, so when the sheets are brought together, there is a tight fit and minimal voids in the gap. To achieve this kind of geometry, there's a couple of options for cutting the strip ends to provide a clean square cut. The most common method is to use a precision shear, which is shown on the left. More recently, laser cutting has been used for this purpose. They each have their advantages and disadvantages. The apparent maintenance cost advantage of laser cutting has drawn much interest of late. But this is a dirty process, and that has a fairly high operating cost when you start looking at gas consumption. A close look at the total cost of ownership may surprise some, so a review of all costs should be undertaken to determine which is really the best suited for a given application. There are two options to be considered for the laser source in laser welding. The one that has been in use almost exclusively for the past decades is CO2. In the last few years, the welding manufacturers have been offering solid state lasers as an alternative. These two laser types are quite different in their optical characteristics and each have their own unique set of processing characteristics. Which laser is best is a subject that is quite involved. An in-depth review needs to be done to understand the implication that each has on weldability, reliability, and safety. What goes into the welding recipe? A recipe for a laser welder has a number of different parameters that can be adjusted to produce a good weld. The key factors are laser power, welding speed, focus position, and gap between the strip. If the machine has pre and post heating, the power settings for these are also required. If the machine uses laser cutting, then again, the power, cutting speed, focus must be set as well as a gas flow rate. There are as many as 15 individual parameters in each recipe. Recipes may vary between material types that they're joining, the thicknesses, and the combinations of material types. It's not uncommon to have over 2,000 recipes for a machine, with 30% of these in regular use. Recipe development is a long and tedious process and requires a good understanding of the process to optimize. Laser welding is not perfect. It can produce bad welds if the process parameters are not properly tuned, or if there's a problem with the machine. Often there's an issue with something on or in the material that affects the welding. The net result is a bad weld. The most common defects that can be categorized as either underfill, reinforcement, lack of penetration, porosity, or mismatch. There are a number of tools that can be used to detect these defects, but I'll leave that subject to our next presenter to delve into. If a laser can weld practically any steel together faster and more reliably than other welders, why not go with them all the time? Well, it comes down to cost. Laser welders can cost up to 40% more than a seam welder. Does your process need all that capability of laser welder? Or can you use a resistance welder or other coil joining technology instead? The laser adds an added risk factor to safety of those working on it. There are stringent regulations regarding protective devices and training that are required for a laser welder, that are otherwise not required for other types of welders. These must be considered. Finally, the laser adds an added layer of complexity to the operation and the maintenance of the machine. Additional training and new skill sets must be developed to maximize the benefits of the machine to sustain its inherent capabilities. Well, that brings me to the end of my presentation. I hope you got something out of it. I'm now open for questions. Oops.
All right. Let me see over here. I think there are still pending questions for Blake, which I think I'll get back at the end of the seminar. But Denny, I have two questions for you.
Okay.
One is, what type of welding can be used for joining gauges with differential thickness of more than 3 mm? I don't know if it...
I don't think there's a welding technique that can handle that. I'm not sure about plasma, whether that would be any more capable than a laser. Pretty much anything that you can do with plasma, you can do with a laser. So more than 3 millimeters, and that's quite a large jump, I don't know. I can't say. I don't know for sure, but 3 millimeters tends to be a lot.
Okay. So just adding to this question, and this was another question I asked, what is the difference of thickness and width which can be welded?
That's pretty much that 3 millimeters is the most I've ever seen when combining two pieces together. Now I was talking about something that was 2 millimeters to 5 millimeters. I wouldn't want to be doing like 0.5 millimeters to 3.5 millimeters. That could potentially be a problem. But you know, in the heavier gauge machines, I would say 3 millimeters is the max.
Okay. Okay. Can laser welding, can we use filler wire for laser welding?
Absolutely. So this is one of the beauties of laser welding is, and I mentioned it in my presentation, is that it's easily adaptable to wire fill or using a wire feeder. And as I mentioned there, it allows you to dilute the two materials that you're welding together. So if you've got some very high carbon steels or some silicon carbon steels, the filler wire is quite handy. It's used in stainless steel as well. And also in some cases, and I ran into it when I was working at ArcelorMittal Dofasco, sometimes you can have issues with a particular kind of material, like a very, very low aluminum or something, and the filler wire would be useful in bringing up the aluminum content to allow that weld up. But that was quite a unique material that we were working with, and not commonly seen. But for sure, using a wire feeder on a laser is quite common.
Okay. One more question. What is the maximum tolerance of gap typically okay for laser welding?
Maximum tolerance for gap. It's not a heck of a lot if you're not using a filler wire. The filler wire gives you a lot more flexibility there. So as far as a tolerance goes, I would say probably less than 0.05 millimeters. If you can hold that, and that's why, you know, I try to stress in my presentation, you need a very stout machine that is very well controlled that can deliver this consistently. Because if you have a machine that's got a lot of slop in it, or over time, develops wear, these are problems, because you got to be able to hold that kind of precision or accuracy and positioning of the gap under the laser. Otherwise, you miss the gap, and you only have maybe 0.3 millimeters, less than that, 0.2 millimeters. If you miss the gap by 0.2, you're looking at a problem that you can't see very well. It's called seam the gap. I didn't get into that defect, but you'll think you've got a good weld, and a lot of the welding quality controlled technologies don't see it, and you end up sending a weld in a line that's not welded.
Okay. All right. I think we need to move on with Alex. I'm sorry we couldn't answer all the questions typed in, but I request the speakers, you can check the Q&A section, and I guess you would also have the access to type in answer, and if it applies to you, I would say that you can feel free to type in the answers from all our listeners over there, because I cannot ask all the questions because of time constraints. So
Thank you.
Thank you guys for the questions, and thank you, Denai and Jenny.
Benny.
And move on to Alex now, and he's going to present on current and upcoming technologies for weld quality verifications.
So I'll stop my sharing and leave that to others now.
Okay, let me see. There we go. Everything all right?
Yes.
Okay, so welcome to all the attendees. Thank you very much for taking the time. I guess we're reaching soon to noon, so I'll try to be fast. Thank you for the opportunity and try to meet the expectations. Denny and Blake made a good job. So today we're going to talk about inspection of welds, both seam, overlapped, and laser keyhole. I myself am far more experienced in laser UT than in welding itself, even though I've been in the industry for quite a while. So I'm sorry if I make some small mistakes, but I'm trying to focus on inspection mostly. So right in the hot of the topic, so failure causes, there are many. It could be wrong or non-optimized welding parameters. It could be drift in voltage or pressure. It could be drift in laser alignment, laser energy, surface conditions, overlap, cut, many different causes that lead to different failure mechanism, which could be a plain cold weld, a brittle fracture, an insufficient weld area, nugget problem, localized defect propagation caused by voids or inclusions. 100% prevention of weld failures is not a simple challenge, but weld breaks, they cost so much in productivity, it's worth to try. To be short today, I was aiming to look at everything that could be related to quality control. I would have busted my 15 minutes. So I'm not going to cover embedded sensors that come with the welder. These are basic. I think they're all offered and they're quite important. I will not cover pyrometers or profilometers because I won't just have enough time, but I think pyrometers are widely used. In the end, there are no technologies right now that can replace the human decision. And the goal here in our topic and in Technar's mission is to completely replace the decision-making by having a technology that inspects the volume, the whole volume of the weld. And that, to our opinion, has to go through ultrasounds. It can be added to laser cameras and profilometers, but ultrasounds is the only real way to inspect the volume. I will start covering the topic using the EMAT ultrasounds, which has been there for quite a while. So EMATs, for those who don't know what it is a non-contact laser, non-contact UT. It uses magnetostriction when you have a ferromagnetic material, or it combines magnetostriction with the Lorentz force, which is a interaction between eddy currents and magnetic fields. It uses that to generate a stress in the material that propagates sound. It is mostly used to propagate what we call lamb waves, which is guided waves that can travel actually pretty far in the strip. it needs to be in very close range with the strip when you do EMATs. This magnetic field gets weak as you get far from the steel. So the EMAT technology, which is widely used, needs to be in very close contact and needs to follow the strip. Now, the Interspec is the company that's marketing a product. Rest assured that all the content I'm showing today has been vetted by Interspec themselves, and they actually provided the next few slides. So it's in full transparency. So the Interspec product will actually guide a wave, and it will measure any backscattered sound from the weld. So it could be a lack of fusion, it could be cracks, it could be porosity. Anything that's there will, trouble the ultrasound and send some back to the detector. So it's a pretty simple concept. The detector is about 4" in width, so it cannot be exactly inspected while we're welding. So actually the grippers need to move back a bit. So typically the sensor will scan on its way back because one of the grippers will have made room for the EMAT to get close to the strip. What you see on the right is actually the teammate product. I know there are two systems running in the galvanizing world. Interspec has sold many UT EMAT systems. Not to be mistaken, it's been there for quite a while. But keep in mind that EMAT is a non-contact technique. It measures the volume of the weld. It detects porosities and disbonds. It also is self-calibrated, which is quite important. In UT, you need to know how much sound you have generated. That can vary a lot depending on surface conditions. So the teammate actually samples the sound going towards the wave, the weld. So when you get the back scattered intensity, you can normalize that with what was sent, and you can have a normalized reading. So here is actually software from Interspec, and upper chart is the welding parameters. We can see actually a change in the welding current, and the lower chart is the backscattered sound in percentage. So in this case, it's a good weld. There was no strong backscatter whatsoever, so it's a weld that's ready to go through. And here's a case of what we could consider a bad weld. Again, there were some changes in the welding current here, as we can see in the upper chart. And in the bottom chart, we got 3 spots, at least that, backscattered sound enough for the operator to say, this needs to be re-welded. It all depends. The threshold it depends on the recipes of the clients. From then on, it could be an automated decision or it can be a human decision, but at least it's a relatively reliable inspection of the volume. Now, the other topic, the other UT technique that's been there for quite a while is laser UT. So laser UT has been invented in the 60s. It's been industrialized in the late 90s. And it's also a UT technique that's non-contact. So basically, we just focus the laser on the surface to generate sound. It's a pulse laser, and we listen to any echo coming back with a second laser called basically the detection laser. The benefits of laser UT that it generates a very, very, very high frequency content, like a shock wave, and it can basically measure very fine structures in what's to be inspected. It can also be, focused on very small spots, so we can know exactly where we're generating the sound. Also generates all 4 main acoustic modes, so longitudinal, shear, surface, and plate waves. So you got all that in a single shot. It is not affected by the movement of the target, by the temperature of the target, by the roughness of the target, or by the orientation. So it's quite rugged for industrial applications. Not allowed to talk about price, like it was said, but it's a double laser technology, so it is not cheap. If you can do it with traditional ultrasound, well, that's what you need to look for, because laser UT is an advanced technology, but it's really mature. As you can see on the right, that's a Technar laser UT system. It's very bulky because it's made to be super robust. We installed those systems in seamless pipelines, and we measure the thickness and eccentricity of the hot pipes actually after elongators, piercing, or sizing mills. And this goes through up to 50 millimeter of steel at 1,000 degrees Celsius. So, I mean, it's an industrial technology, and it can be miniaturized to be quite small. In this case, there's space, doesn't matter, but it's an example of a industrial laser UT application. So here's a small schematic of how does it work. So we shoot the laser spot, and basically the detection laser shines for longer period of time, enough to capture the ultrasound. This is a real laser ultrasound A scan, as we call them, and you can see that the resolution of the echo is quite high frequency. So it allows for a lot of analysis, namely it allows for attenuation measurements that can reveal the microstructure of the material, which is a bit, it's like the second wave of using laser UTs, not only for defect measurements, but for microstructure. So I'm going to talk about two ways of using laser UT. One is what we call pitch and catch. Pitch and catch is what would be definitely used for laser butt or keyhole welding, because there's no, it's not relevant to just scan on the weld itself. You're just going to pass sound through it like the inner-spec product would. So pitch and catch is laser on one side, detection laser on the other, and we just send the sound through it. It's going to measure the whole volume of the weld. It's going to backscatter. It's going to attenuate if there's any porosity or lack of fusion. This is an example of a scan in the pitch catch mode on an overlap seam weld. And you can basically see the sound picked up on the other side for a good weld. And now there's no advanced frequency analysis. That's just a mashup of lamb waves and longitudinal and shear waves, but they actually just basically by the amplitude of that, you can see that that's a good weld. In the center, that's a weak weld with much less sound. And basically on the right, it's just a complete lack of fusion. So it's pretty bad. There's no sound going through at all. You can see that it can be color coded. You can see the laser spots. We can basically generate and detect quite close to the weld itself. So it can be, installed right at the welding with the grippers at their standard positions. And it is not affected by the temperature of the strip. The second method I'm going to talk about today is called overlap. So when we say overlap, is that the generation of the sound and the detection is done at the exact same place. So that can allow having basically a full 2D scan of the weld as it goes through. So for the next slides, I'll be presenting 2D scans of welds that were provided by our partner. First thing we did is we actually looked at 4 different welding parameters, from absolutely sure that it's good to absolutely sure that it's not good. They were bulge tested, and only sample 1 actually failed completely. The other 3 were good. And there's 2 different readings of UT in overlap mode presented here on the right. One is basically just time of flight that measures the thickness actually of the weld. And on the right side, it's the microstructure. We can relate that to grain size, recrystallization process due to the amount of heat. So very clearly, just looking at time of flight, there was actually no sound at all collected in overlap mode for the bad weld. So we could actually, it was positively working just using time of flight. If we push it to microstructure analysis, we can also see that there was nice recrystallization on weld 3 and 4, but basically very little recrystallization on weld 2, so probably more brittle, smaller grains, as we'll see later. And actually microstructure analysis was irrelevant on weld 1 since we had actually no sound because of the lack of fusion. So next step we did to our partner, we said, can you produce 10 welds between the parameters of weld sample 1 and weld sample 2 to see how, granular is the threshold for determining bad weld. So I'm not going to show these 10 welds, but the 10 welds, on the chart here, you see there's 10 samples. Those were the 10 welds between good and absolutely bad. And they were tested by the bulge, by the parameter, and also by just basically visual observation. What is funny here is that the bulge test revealed that the threshold for rejecting based on parameter and visual observation is actually much higher, and that many welds can go through, and that they are actually re-welded. So that's a loss of time in a certain way. But if you look at the UT testing, the UT testing actually was in better accordance with the bulge test. We could see very fine recrystallization for the green welds. The ones that could maybe have passed through the process were showing some irregularities, and we could also be in accordance with the no-go ones that were actually very badly welded. If we look at microstructure, when I say microstructure, those are weld number 10 and number 2. So we could see that number 10 was a good weld. There's no cracks, and you can see with the eye that the grain structure is different. There was enough heat in there to have a very mature recrystallization. And for weld number 2 there, although that there's visually cracks there, you can see how fine the grains are, and that this weld was not really hot and didn't have the chance to grow some nice grains. So it's basically, it's in accordance with what the overlap method also provides. So it's a bit more advanced method. But the overlap method needs to scan. So these nice 2D scans I've shown take quite a lot of time. We still are aiming at a product that inspects the weld during the welding. So this is basically what looks like the system. So it's going to be scanning, you know, back and forth to cover the whole weld. Our experience shows that if it's a bad weld, the defects actually are all along the weld, mostly for lack of fusion or bad recrystallization. So this technology should pick it up pretty nicely. So summary is that laser UT, there's 2 approaches. It's pitch and catch, which is simple. It detects lacks of fusion or localized defects. It is the way to go for laser keyhole inspection. And for overlap UT, it's a bit more complex. It requires scanning, but it detects lack of fusion and localized defects, but it also measures microstructure related to nugget and grain growth. And also probably will be able to measure the overlap width since we have a 2D scanning. So, and also laser UT can be mounted right on the welder. So that's about it. Thank you very much. My contact information is there if you ever wish to contact me.
Okay, thank you. Thank you, Alex. Any questions for Alex over here? One question real quick. What is the time taken to scan a weld using the laser UT?
So it's gonna be transparent because we're building a system that's gonna be mounted on the welder. So there's no additional time.
Okay. Has your partner company put your product into their operation after testing was successful? Also, what method do they use? Pitch and catch or overlap?
Yeah, so right now we're aiming to release the product end of this year, maybe early next year. So we still have, the stage of the technology is prototype and it's at Technar. It is not on any site at all right now. So we're basically working with partners that are sending in some welds, and we're closing in mature products, and we want to get that out as soon as possible. And there's a chance we roll out those 2 methods right off the bat. It all depends. I mean, everything's going to happen this year. It's a big year for us, and we have partners that are waiting, that have been very patient and waiting. I think there was one of them online here, so very patient at waiting our prototype. So we're going to install at least 1 system as soon as we can. Maybe a second one. You know, we're open to work with partners and open to receive some welds to do some qualification using our station here. But right now it's not on site yet. So, I mean, we're going to announce that as soon as it's working.
How much time does it take to calibrate the UT?
So that's also an unanswered question. We think that we're going to also normalize the sound, same thing that Interspecs does. So I think that the normalized readings should be fairly easy. I don't think there's going to be as many recipes for establishing the threshold that there are recipes for welding. You know, some lines have up to 200 different recipes to weld all of those different advanced high strength steel. I don't see that being as complicated with laser UT, but it's a question still to be answered.
Okay. I think last one for you, Alex. Ultrasonic versus UT, like price or quality wise, what do you think?
I'm not allowed to talk about pricing much in this.
That's correct. My bad. I shouldn't have. Okay, probably another one. What is the maximum material speed possible for laser UT pitch and catch?
Well, the pitch and catch can go at least 1 to 2 meters per second. It's going to be basically, we're going to roll out something that's going to be 100 hertz, so 100 shots per second. So that it all you know, if you go a meter a second, then you have 1 centimeter between each shot.
Okay. think these are some old questions, and Blake and Denny, I guess you guys have answered most of the questions while like typing. You answered them while the other presentations were going on, I guess.
I've tried to. It's there's been a few here. I'm not sure if this box is going to stay open for a bit. I'd like to get to address them all, but yeah, some of them are quite involved. And there was one question about
not an easy answer to them.
yeah, questions about solid state versus CO2 lasers. Go to page 56 of the February AIST Technology magazine, and I think there's about a 10,000 word article that I prepared with my associates from MEBOC on that. It's not a simple question.
Well, and there were some questions about ranges of material thicknesses to join, and yeah. I'll answer that from generally speaking, from a resistance welding standpoint. We try to keep it to about 2 to 1 for the ratio of thicknesses being joined. You can go heavier with resistance welding if it's low carbon steel, and if it's, you know, this type of steel that will fuse together without going to an abnormal level of force.
Yeah, I answered that question as well. Basically, the question was, what do you do if you go over 3 millimeters? And that's quite a big jump, right? So
I would agree with
transition coil. That's one that comes in there, right? We were successful in that our trials, or actually we were in production with quite an elaborate arrangement that MEBOC had prepared for us at the FASCO. And but the bottom line is, what can you do with it? We were tied into a cold mill. The cold mill couldn't roll it. MEBOC actually had a milling machine built in to our welder. It's the only one that they've ever done that with. And so to give a smooth transition, but we couldn't roll it. So, and that milling head was just a maintenance headache. So I was happy to get rid of it. Anyways, that's a long story, but
I agree with Denny. That 3 millimeter jump is pretty severe.
Yeah, we don't even like to talk about it.
It couldn't be done with weld trials and the right weld parameters, but that would be difficult.
Yeah, it's just, when you're working with something that's so light on one side and heavy on the other side, like how much heat do you put in it without blasting away the light stuff, right? But you have to have enough heat there in order to fuse, to make a good fusion joint, right? So it comes down to the physics. So I basically said, put in the transition coil, put in something in between, right? But because you're not, other than like if you're tied into a cold mill or maybe some other processing lines, yeah, it gives you that added flexibility of scheduling the line. And I think, that's one of the big benefits of lasers is that you can weld practically anything to anything, right? Throw in some filler wire and you can do almost anything. But the filler wire is not the answer to everything. I don't like really pushing that. It slows down the process for one. And you've got now stuff to deal with, wires that don't go where they're supposed to go. So that's another maintenance headache. So in the machine that I worked on, the 2 machines I worked on at the FASCO over 14 years, we didn't have wire feeders, and we were welding a lot of different stuff together. Some of the companies that I was supporting through ArcelorMittal, they had wire feeders, painted whatever, and they're constantly fighting, trying to get alignment correct, and not the solution. You slow down, your cycle time goes up. And you're adding complexity. Keep it simple is the key.
Okay. Ken, there was a question regarding whether the question and answers will be distributed, ones which are typed back.
Unfortunately, I don't know the answer to that. I'll find that out and let Stavros know in particular, and hopefully we can let everybody else know also.
Also, at the end of all of our presentations, I think our contact information is there. In my case, it's for my colleague, Matt Keller, who was originally going to do this presentation. And So, but Matt will answer any questions that come out of this, and I'll make sure that that happens.
Okay. So I think it's time to wrap up. Then, like Blake said, everyone had their contacts. Blake, Alex, and Denny had their contacts at the end of their presentation. So please feel free to email them for any unanswered questions. I think these guys did a great job presenting and answering all the questions via typing or via the presentation, via the webinar itself. Thanks a lot, guys.
You're welcome.
Thank you. We appreciate the opportunity to talk to everybody.
Absolutely.
Part of this webinar. Thank you.
Yeah.
Thank
Yes.
you all.
Thank you.
And
Thank you, Ken, for getting us involved.
Yes.
And that should wrap up this webinar. We appreciate everybody attending also. And Nikhil, you did a great job. Guys, you did a great job presenting. And with that, we will end the conference, the webinar. Thank you all.
Thank you, everybody. Be safe and healthy.
See you guys later.
See you
Stay
guys.
safe.
Bye now.
Thank you.
Bye-bye.
See ya.